everybody. So I've never spoken in front of so many people. So if I do mistakes, please just correct me or destroy me with Slido afterwards. But I try to explain stuff first, and then you can go on. So today is a PowerPoint working. Wait, 1 second. Yes, OK. So today is a really famous birthday. Does anybody know who was born on November 29th, 170 years ago? Maybe not. It's Mr. Fleming, and he was a Briton engineer who developed something really interesting, and those are called... The presentation is not really going well. Wait a second. No, that's not my presentation. That's not my presentation. That's like quantum computing. You have multiple states, and you do not know where you end up, right? So... Wait a second. Duplicate.
Let's try with clicker.
OK, let's try that. So, yes, OK. So this is Mr. Fleming, and he was the British engineer who designed the so-called Fleming valve, also called vacuum tube. And it was the beginning when we were able to kind of manipulate how much electrical current is flowing through stuff. And it started everything that we know nowadays. It's the digital world, or like actually the society in general. And the cool thing is you can actually relate it one-to-one to transistors, but transistors nowadays, luckily, are much smaller than vacuum diodes back then, and you can line up to 10 transistors in a row and get to the size of 1 bacteria, which is actually quite nice. And this is why we can get Moore's law working, because Moore's law, everybody's probably familiar with it, says that we can double computing power every 2 years by making stuff smaller and more efficient. But the really interesting questions we have to ask is, how small can we get? Because we cannot scale atoms, right? But people and quantum computing asks if we can make atoms computers. And this is actually what I want to talk about today. But I'm not a hardware engineer. I come actually from the field of chemical engineering, and I stumbled across physics because at some scale, all the science comes together in like singularity. No. Not really, but the stuff I'm trying to work with are actually something that we call unicorns in our school sometimes, because it's actually quite hard to be a chemist if you work with tiny stuff. And each atom has an outer shell of electrons, and those outer electrons determine the characteristics of the element. That's why we have the periodic table. But those outer electrons are not easy to predict. And if you look at this periodic table, we have about 80 stable elements, then some stuff that was made up in particle accelerators. And many are important. And we have one equation for all of this to predict the electrons. And it is the equation that Schrödinger once came up with. He himself doesn't really know how he came up with it. And if you look at the Schrödinger equation, you have this thing here. Wait, pointer? Pointer? No? OK. But it's the wave function. And the wave function basically describes the most important stuff. But it only works for hydrogen, because after this, we have 2 large systems that we need to solve. And computers will not ever really be able to solve this for lithium, for example. So the only answers we can get are the answers that we can get from the particles themselves. And I never thought about quantum computing being something revolutionary until I actually found out that I'm already familiar with the operations that we do on quantum computers. One of them is NMR, which is nuclear magnetic resonance. And there's a principle behind chemistry where the electrons in the outer shells kind of shield the inner nucleus. And if the inner nucleus has a spin up or down, and you put it into a magnetic field, it aligns itself accordingly. And there are actually 2 steps and 2 different energy niveaus where it can be. And you can intervene and put it into a different energy state with electromagnetic waves. And this is one of the simplest. And obviously, the unicorn does not, it's not an electron this time, but it's actually the nucleus. But the nucleus has its properties through the electrons that align with the magnetic field and shield it. But we see that there's one state that it does not really want to be in, and one ground state, the Y state, that it's more likely to be in. And the phosphorus atom is actually one of the first quantum computers to be built. That's the first and simplest principle, to put just one foreign atom into a processing chip, and then you can try to find the different energy niveaus and operate on them. And this is what chemistry looks like. We never think about quantum computing. Actually, we just want to look at our molecules to find out how they look, because it's hard and we don't have a microscope for it. And this is a really cool NMR spectrum where all of these peaks align to different energy niveaus, and this was called by Magdalena Lederbauer, and she's a really cool chemist. I also would recommend, if you someday meet her, look and try to find her. But I'm quite nervous, sorry. But the 3 questions I want with you to find an answer today is now, what are quantum gates, how to program a quantum computer, and what is the hardware behind a quantum computer that's not like NMR that we all know. And I tried to prepare a little experiment because, like, I'm an engineer, right? We cannot really calculate, but we have to do experiments first. And I will try to show it to you. So, maybe. So we have polarizers, and if I take one, you see that there's light coming through. But if I take the other one and line it horizontally, you see that it's getting black totally. And that's nothing really surprising, because actually polarizing filters just filter out waves that come not polarized this way, but polarized this way. So you actually get half of the light. But the really cool stuff is now if you put a third filter in. Because if you put it in the front or in the back, nothing really happens. But if you put it in between, suddenly you can see through again. Can everybody see that? That it's getting lighter? Little bit, little bit, little bit. Okay, it works much nicer with better foils, but this was, yeah, okay. So that's actually a small quantum computer, because we operate on the state of the photon. Polarization is something that is actually a quantum state, and polarization is something that is in it on the photon. A photon cannot divide anymore, so it's something that is quantized. It's a quantum state. Okay, so this is our polarizing filter, and we see that the photons can travel through, nice. And we also see that the photons cannot travel through if they go the other way. And if we put them after each other, as we saw, we will get black, because those either get absorbed in the first stage or in the second stage. Nothing weird about that. But the calculations I would try to do with you today is if we put in the third filter, because then somehow they get through again. And the easiest answer would be to say, okay, it's just in between, it's just a mediator, but it's nothing mathematical. And quantum computing actually relies on just mathematical calculations, and I know that probably all of you are familiar with matrix multiplications, because if you're interested in AI, you will not be able to get around of this. So, Okay, so as we saw, the light that's coming to all of us is actually polarized in many directions, and we will just plot it into 2D, because our filters were also only 2D, and we will get to 3D afterwards. So the thing is that it does not really matter if the light is going this way or this way, right? So it does not really matter if it's 180 degrees turned around, so we will just look at the half of the circle. And if we have now a photon that's coming and it's not aligning with the direction of the filter or the absorption direction of the filter, then we have somehow a problem, because a photon cannot split and something can be absorbed and something can go through. You can imagine it like kind of a sack full of sand. If you have a big enough sack of sand, you can divide it any longer, and then you come to one grain of sand. And if it needs to go somewhere through a mesh. It has to divide. So what we actually see is that it then has to decide whether it be X or Y. So whether it goes this way or this way. So in our case, if it goes the vertical way, it goes through to UIs, and otherwise not. So, good. But the cool thing is, now we're doing calculations. We rotate our filter, that was the one where I just showed 2 filters, around 90 degrees. And if you do a little bit of trigonometry, you find out that you get the previous axis to this state by multiplying with this matrix. And because we rotate by 90 degrees, we put in an angle of theta with 90 degrees. And this is our new matrix. And you see that the first 2 now show where our x is, and the other 2 show where our y is. So first column x, second column y in this case. And then we also have the photon. And the photon at this whole process was not changed. Only I changed the filters. So what we now do is we take the initial state of the photon and multiply it with our new with our new vector space, and then we get a new vector. And now we see, probably, that the first thing is x. It was also x before. So it's a little bit, and second one was y. And we know that x is always going to be absorbed, because the characteristics of x do not change. Just the direction of x does change. And this is why we don't get a photon. Because now, all of the photons are now not going to be measured any longer, as the measurement apparatus was turned around. And it's getting a little bit difficult now, but stay with me for a second, because then we come to the most crucial point. If you don't want to follow the calculations along, it's fine. You can go on them a lot longer, but the most crucial point now comes. So we have, for the filter that's 45 degrees, another orthonormal basis. Then we have another quantum state, and now we see that they are in a multi-position. So it was like the one that I showed before. It should either decide x or y, but it actually does not have if it's 45 degrees. And then we go on with the second filter in the end, and then we see that somehow we end up with this formula. And it again gives us the wave function that we showed by the Schrödinger equation previously. It is not 100% the same, but kind of similar. And then if we want to have the y, right? The y is our photon. We want to have the photon. So if we want to see if the photon goes through, we can take the square of the minus 1 over root 2, and then we get the probability of 1/2 of detecting a photon. So previously, we had the 0. Do you know the 0 in the vector that we had? 0 probability, because 0 squared is 0. But now we have minus 1 over square root 2 squared, and this is 1/2. So we get photons through more filters, even if we don't get in from less filters. And now is the 3D part, and this is getting a little bit more fun now, because it's more easier to visualize with another matrices. So this is called the Bloch Sphere. It was named by a really cool physician who also got the Nobel Prize, and there are multiple states that are really interesting for us. And on this whole sphere, we can put any qubit and do calculations with it, but in the end, we can only measure the state 0 or the state 1. And at the calculations, however, we can rotate around, for example, theta, or we can rotate around the other phi, and this is what quantum computers do. They use the time in between measurements to do fun stuff where we can never interact with. So we have somewhere our wave function, and it can be all over the sphere, but in the end, it has to end somewhere where we can measure it. And the operations that we do in the quantum computers are called gates, as also in normal logic gates, but we actually represent them with matrices. So for example, identity matrices, when put on the quantum computers, is exactly the same, because nothing changes with an identity matrix, right? Okay. Then we also have the polygates, which actually rotate around different angles and different axes. And those, you see, take the initial state, which is always 0. If you start quantum computing, you will recognize that it always starts with 0, and rotate it around different angles. And you see that x and y end up at the same direction if you rotate around 180 degrees. But z, for example, does not, because it just rotated around itself. The most important is the Hadamard gate, because this gives you the probability to finally get into a place on the sphere which is not the north or the south pole, and then you can go on and do fun calculations by rotating around anywhere. And this is where our nice formula comes in. The Q gate, that is also nice if you work with multiple states. It's called Lcx Gate, which is actually control X gate. You can also do a control H gate or a control anything gate. And this is like an if function, so you measure one qubit and then put it on another qubit. So if it's 0 or if it's 1, you do a calculation on the other one. And you can interchange the matrix of X with Z or whatever. And the measurement is the most important, because when it does not matter where your qubit is, it then has to be put somewhere where you can store it. Because you cannot really store data much longer on qubits, because qubits are normally atoms cooled to low temperature, and at this low temperature, they're not 100% stable. So that's actually a really big problem. But summing up, the most important thing that we got from the calculations for this moment is that we have a certain function with certain factors, and if you take these factors, which are most important, and square them, you get a probability of your measurements. And this probability of your measurements is what gives quantum computing its power. Because, for example, if you have 2 qubits, you would normally have 2 bits and 2 informations. But if you take them in quantum computers, you have 4 possible states that you can be in. And for each of those states, you have 1 probability of measuring them. So if you measure those 4 different states, you get 4 different answers. So for 2 bits of information, qubits in this case, you get 4 numbers. And it scales up. For 3, you get 8. So that's where the power of quantum computing comes in. I have never really thought why actually we can get so many numbers. But actually the numbers that we can get from quantum computing comes from running experiments and getting statistical data and probabilities and then applying them and looking back at how the environment changed our quantum sphere. So let's program something. It's not an official word yet, but maybe we can do it. So, oh, I also thought about pro-quanting, but I'm not sure yet, so yeah, let's try it. So the cool thing is that many services actually offered online or in the cloud, and IBM does some really good job with this at the moment. But we'll look at just one Jupyter notebook. So what I'm trying to do with you today is not to plot one of these qubits on these Bloch spheres, because that's actually stuff that helped me visualize a lot better how my operations work. Because if you start with quantum computing, you have in the end, in the beginning, no idea, and in the end, you're looking like, I kind of understand it, kind of don't. And the more easier it is to visualize, the more easier it is to explain it, the more easier it is also to work with it. So the library that we import is called Qiskit. Wait. Sorry. Yes, sorry. My fault. Wait, it's no. Wait. Okay, so we import everything from Qiskit, but we also import no, sorry. Qiskit tools. We import visualization. Is it right? I need to duplicate my, otherwise I'm going to be quite sorry. No. So, okay. We will try again. So now it should be better. Let's try to get this one out of here. No. Escape. Yes, much better. So. Good. Yes, okay, perfect. Thanks for staying with me. So, okay, we want to plot our multisphere, so we import the multisphere thingy, multi-vector. So, okay. So, and then it's actually quite easy. First, we have to build a circuit. Then we apply some operations on the circuit, and then we measure the circuit by running it on a simulator or on a real quantum device. And then we will get back the results, and we can analyze those results. That's what we are going to do. So first, we build a circuit. If we have imported this stuff, without a U for, of course. So we then, typos are my friends. So, good. We build a circuit. And it is called easy quantum circuit. And then we have to give 2 parameters, and those are how many qubits we want to have and how many classical bits. And you can kind of imagine that on the qubits, you do all the calculations, and you store your data in the classical bits. So we take just one, because it's easy to visualize, and then we can also plot our circuit. So if we say circuit.draw, we now see how it looks like. So we have 1 qubit in state 0. As I said before, we start with 0, and also a classical bit in state 0. And we can also do it a little bit more fancy. We can also say output equals lib. So, nope, false. So, and then we give, it's more visualized. But the cool thing is now that we can apply a gate to this. And for example, if we do the Hadamard gate, which gives us the superposition between state of 1, we just have to write circuit H and give the qubit on which we operate, which in our example, as we only have 1 qubit, is the beginning of the list, so it's 0. And then we can make circuit draw again. And I also don't even have to write it in one cell, as it's a 2-bit notebook. And we see that our Hadamard gate was applied. And then we have to get our backend, and we will try to run it in a simulator, because later we will see that actually the quantum systems of IBM are most of the time really used by researchers and really booked out. So a simulator equals AIR. This is one of the backends that provides many functions to you. There's also Aqua. Aqua is really cool if you do AI research. We will come back to later afterwards. And they also have Terra, which is more like the foundation that builds up on it. So in quantum computing systems, you have to have multiple layers, because quantum systems are not something a computer directly can operate, but you need some lasers, electromagnetic equipment in between. So yeah, let's get backend. And then we have our, here below I wrote down which ones we have at the moment visual. And state vector, for example, is the one that we're trying to use. State vector simulator. So, okay. And then we have our results that we will get if we execute our circuit. And we will execute it on the backend, and our backend equals our simulator. And from this, we have to get the parameter or the function result. So, good. Let's try to run it. Nice. And then we can plot our results. And as we imported plot Bloch multivector in the beginning, we can now say state vector equals our result, and then we get .get state vector. Nice, no, so. And then we can either print the state vector, for example. If you don't want to do it, you can also not do it. And then we get the matrices that I showed before, and then we can also do plot Bloch multivector. And yeah, on our state vector. So this should be fine. Yes. And then we see that our Hadamard gate was applied, and our qubit was rotated from 0 to x in this case. So you can apply any function that you like in this beginning. For example, if we now start with, if we don't apply anything, so we just say, okay, we just want a new circuit, then we start this way. We do this again, and we see that our qubit starts at 0. So you can, what I would encourage you to do if you start quantum computing is to try out all the gates that they are, because then you kind of visualize what they're doing. And it's more easier to do something if you know what you end up with. And I also have a 2-bit notebook prepared somewhere, which I could maybe put up on GitHub, where all the quantum gates are explained a little bit more in detail, and you always have an example how it was going to look, and in the end you can also have and run them on and visualize them if you don't want to do the coding. And also it's a really cool function that most of the time is not in the documentation, is the CIF function. And CIF is that you look at a classical bit and only do it if data is stored. Okay, so good. I'm really sorry. That was a lot at one point, but why do we do it? Because, for example, Austria and China are the only countries at the moment that are doing space quantum entanglement and space communication, actually, with quantum qubits. And those send photons to Graz, or to Hong Kong and Shanghai. And they're doing really cool stuff with this. So the quantum gates that are applied in Graz are actually the same that are applied at quantum computers elsewhere. And those are the most ones that are secure. So the thing is that you want to bring a secure key from one point to another, and the only thing, if you don't want to be broken by a quantum computer, is to do it by a quantum computer. This is called the Mizio satellite, if anybody's interested. Good. Why is it good for AI? If you have multiple functions and you overline them, then you get, in the end, the one that's most stable as an outcome. And you can kind of relate to this if you have multiple wavelengths, some will cancel out if they're not in phase, and they will increase in amplitude if they are in phase. And Google is currently trying to do this, and they're also building a quantum computer, also the one that maybe has reached supremacy. And they're saying we're developing a framework to implement a quantum neural network on near-term processors. We're interested in understanding what advantages may arise from generating massive superposition states during operation of the network. And there are also IBM, for example. I also put down the Aqua and D-Wave doing this stuff. And the thing is that we are still in a part of total investigation. We're still in a part where we have, there's a Qiskit Slack channel, by the way, and you should join it if you started. And there are people discussing stuff like this. this is like the 1940s when they were working out how to do an 8x16 divide on the hardware they had. And then somebody asked, yep, it's like starting all over. And it's like, really, we don't somehow understand how the systems work. And that was, I'm really short on time, sorry, but I want to briefly mention that actually CERN is one of the main research centers where I find out that they work on quantum computers without even knowing that they're working on the hardware that they have to provide. So, for example, they work on really cool superconducting magnets and cooling down systems to points just below 0 degree Kelvin. And those are actually one of the backends that are nowadays used as quantum computers are like. Those are called superconducting circuit, and superconducting circuits are basically miniature circuits cooled down to really low degrees, and the electrons then start to condense a little bit and work as a whole system, and you can modulate them with microwave pulses. So nice, microwave, my quantum computer. The other thing that we use is ion traps, and those are more investigated in the universities because the circuits at supercooling temperatures are more available for large scale, and ion qubits are still really, really, really low in being able to be controlled precisely. But the University of Amsterdam is doing cool research, and also the same system is used in CERN to store anti-hydrogen or anti-protons in the end, because if you have anything anti anywhere, then you have to use a panning trap to really have it in there. Okay. And also, at CERN, you always get to see this. It's the official greeting. So if you meet somebody from CERN, do this, right? And this, interestingly, we know that Fleming actually was one of the people pushing into new kinds of computing because he invented the vacuum diode. And he also gave this freehand rule. So maybe it's also important for quantum computing in the future. But the biggest achievement that my group achieved at science at CERN was that we made a Toblerone accelerator, which was actually larger than one of the real magnets in the collider. And we're proud of this, to say that the Swiss chocolate helped us to be longer than the CERN collider in the part of it. And my task at CERN shows definitely that there actually is still so much to explore, and I know so little about it. And my task was to find and calculate on data that looked at really rare decays of kaons, and those are called penguin diagrams, because the Feynman diagrams, which show how the particles could interact, are actually not really understood, because the masses that you would need for stuff like this is sometimes even larger than the mass you could provide, and sometimes they still happen. So my supervisor said, okay, when I was asking, what are we going to do? And we are trying to break the standard model. And it was like, okay. But I think the standard model is pretty awesome, because particles, through the Feynman diagram, show that they are everywhere at every time, like in a quantum computer. And I learned at CERN that my view of the elements of the world is not really accurate. And I will probably also learn that it's going to be going a lot deeper and more complicated in the future. And that's why I'm actually really happy to start now and have also contacted so many cool people that also are interested in topics like you. I think it's cool that you all attend here today, because it's cool to see the unseen and know the unknown, and then do something that nobody probably managed to do before, because we just believe that there's still something, even if we cannot see it. We still believe in electrons, we still believe a little bit in unicorns, but we don't really want to push it towards an edge where we just fail, because computers not about computers anymore, it's actually about living. And I had to put Austria. It looks a little bit like Austria, right? It's a really nice protein. Does anybody know what it is? No? Okay, that's Cas9 actually. It's the protein used a lot for DNA cutting and analyzing and whatever. And the cool thing is that there are also new tools coming to medicine, and we need quantum computers to find out how those are trying to get folded. Because in the end, some people are trying to find out how to do prime factorization, but what we as chemists and biochemists try to find out is how we can get from this protein origami down to the instructions and down to the paper that it came from, because then we can replicate it and make medication that helps people actually. So this is the last slide. I'm really sorry for all this much information that I gave to you. So one person said already when they were talking about quantum computing and stuff like that, it doesn't matter what questions you ask, you can rely on mathematics. So just shut up and calculate. And thank you. Thank you. Also to you.
So, Thank you. Wow, really, really great talk. Thank you, Alexandra.
Okay, yeah.
Yeah. You've given us a lot to think about. Really great. You've done the undone by speaking in front of such a huge crowd for the first time in your life. Do you want to take a stage selfie?
Yes, definitely.
Yes.
But before,
Please participate in the stage selfie. Do something crazy so that you will have a memorable time with Alexandra. So, yay! 1, 2, 3, yay! Okay. So now, time for questions.
Yeah.
We did run out of time, but I think we can take up a bit of time. You know, pause is
that first one is
unrelated.
really nice. What I want to like to do in the future. Sorry. Okay.
Such questions, no?
Okay.
You want to answer that?
Yeah, I just briefly want to touch the topic. I think also my mother always had a clue of what my sister is going to do, but always when I was asking, like, do you have any kind of idea, or do you think that I'm going to be in any field? And she was like, I always thought there's something new coming up and that they were going to try it. And I think that's the cool thing, that if you're in science, you see that everything somehow grows together. And for example, if you look at colors, you can look at colors from so many different perspectives, and you can go from the chemical side, but also from a more physiological view. Or I can really go down to the scale where I see, okay, if materials are structured in a certain way, like butterfly wings, then you have a structure that's blue, or looks blue, but it actually is gray. So if butterflies are just blue because of their structure. So that's interesting. I think the stuff that's interesting is the stuff that's in between, where people have to talk to each other.
Awesome.
What do you think?
So, let's take just 2 more questions, okay?
Yeah, perfect.
So,
Yeah.
all right. So the second question, and as you know, Alexandra will be around here, so afterwards you can find her. Probably there's going to be a long line, but still you can find her and talk to her in person. Second question, we have 2 more questions. What do you think? How much time will it take until quantum computers can take over correct cryptography?
There are already people trying to do that, right? I showed you the satellite, the Meteor satellite, that is doing this between China and Europe. And the problem actually is that you need the equipment is quite expensive nowadays. So there are people trying to invest in quantum computing, especially telecommunication, because their security is a priority. But the thing is that you really need this expensive equipment, and I think it actually is at the cost at the moment. And also still at how accurate you can get the qubits to align for a certain amount of time. Because if it's not correct and they wiggle too much, then we have a problem. How long? I don't know. I think we know so little. I think it could be in 10 years, but it could also be in 20 years. But if we look at how AI evolved in the last years, we could also say it could be maybe 5 years, 2 years, I don't know. So it's up to you how long it takes, right?
Interesting. Yay. Okay, last question. Is the concept of digital even relevant to quantum computing?
Yes, it is. I think the digital and quantum computing has to be divided a little bit, because quantum computing is more of the experiment that you do, and digital is more like the data you store. And also, I can be in the laboratory and do experiments, but I still have to go somewhere to store my stuff and to have my equipment, and also to have a computer to do some analysis on. So as I also told, quantum computers have qubits and also have classical bits. And digital is where you can then connect also information and stuff like this. So quantum computers cannot do everything. They're good for certain problems, but not for everything yet.
Yet.
Yeah.
Yes. Who knows what will happen in the future.
Yeah.
So that was it for today, or for this talk.
Okay.
Please find Alexandra, and also ask her a lot of questions, follow her on social media, and email her with questions. Have a lot of discussions, and we really look forward to what you're going to do in the future and what the future will bring us. Thank you so much. We'll have a short break.
Thank you.
We'll regroup again at 3. Please, a round of applause to Alexandra Waldherr.